Imagine a computer so powerful it could solve problems that would take today's fastest supercomputers billions of years to crack. This isn't science fiction. This is the promise of quantum computing. We are standing at the threshold of a new technological era, one that could redefine everything we know about medicine, materials, science, artificial intelligence, the fundamental nature of reality itself. Our story begins not with silicon chips, but with a puzzle in the early 20th century. Albert Einstein, Niels Bohr, Erwin Schrödinger. They were uncovering the strange laws of quantum mechanics. They found a world where particles behaved in ways that defied common sense. A particle could spin in opposite directions at the same time. It could exist in many places at once. These ideas were revolutionary and laid the groundwork, yet they were seen as descriptions of nature, not tools for computation. The idea of using these effects to build a computer was a whisper, waiting for the right minds. Richard Feynman connected quantum mechanics and computation. In 1981, he posed a problem. Simulating quantum systems on classical computers seemed impossible. Even a few particles would need a computer larger than the known universe. So he proposed, build a computer that operates on quantum principles, using superposition and entanglement to simulate nature directly. In 1985, David Deutsch formalized a universal quantum computer, able to simulate any physical process and solve certain problems exponentially faster. They imagined a machine that computes with the fabric of reality. A bold vision, where quantum weirdness is a feature, not a bug. The 1990s moved quantum computing from pure theory to experimental reality. Could anyone actually build a quantum bit, a qubit? In 1994, a breakthrough. Peter Shor at Bell Labs unveiled a quantum algorithm. It showed quantum computers could factor large numbers exponentially faster than classical algorithms. A bombshell. Modern encryption relies on factoring hardness. Shor proved a quantum machine could break it in principle. In 2001, IBM and Stanford ran Shor's algorithm on a 7-qubit NMR quantum computer, factoring 15 into 3 and 5. The point: theory translated into a real, physical experiment. Teams explored trapped ions, superconducting circuits, and photons, each with strengths and weaknesses. The race was on. In the 2010s, D-Wave sold quantum annulars for optimization, sparking investment despite not being universal machines. Then Google, IBM, and Microsoft entered in a big way. In 2016, IBM put a 5-qubit chip on the cloud, democratizing access for anyone online. In 2019, Google claimed quantum supremacy, a 53-qubit Sycamore computation practically impossible for classical supercomputers. Now, in the 2020s, qubit counts surpassed the 100-qubit mark, but noise remains. The decade's challenge: fault-tolerant quantum computers via quantum error correction, bundling many physical qubits into robust logical qubits. Roadmaps promise thousands, and eventually millions, of qubits. As we stand here today, October 3rd, 2025, we are in the midst of this transition. The promise is no longer distant, it's tangible, and brilliant minds are racing to achieve it. This essay is your guide to the frontier. The quantum age is dawning, inviting us to see the world and the future in a new light. To understand a quantum computer, start with a classical one. Your laptop stores information as bits. A bit is like a switch. Off is 0, on is 1. Billions of switches do everything from playing movies to sending emails. But solving complex problems can require trying many possibilities, one after another, costly in time. Quantum computers use qubits. Like bits, they can be 0 or 1. But thanks to superposition, they can be combinations of both. Think dimmer switch, off, on, or anywhere between. 2 qubits represent 4 states at once. 0, 0, 0, 1, 10, 11, 3 represent 8. With 300 qubits, you span more states than atoms in the observable universe. The second superpower is entanglement, Einstein's spooky action, linking qubits so their outcomes are tightly correlated. Measure 1 as 0, its partner is certainly 1, and vice versa, no matter the distance. This interconnectedness enables powerful parallel processing unlike anything classical. During a calculation, qubits evolve under quantum gates. When measured, they collapse to 0 or 1 with probabilities you design to favor the right answer. Quantum programming is choreographing interference. guiding a wave of possibilities toward the correct outcome. Superposition explores many possibilities. Entanglement knits them together. Careful measurement extracts useful answers. That is the essence of quantum advantage. Today's landscape blends academic labs, government initiatives, and corporate giants in a fierce race to fault tolerance. Google's Sycamore headline and roadmap target a large-scale, error-corrected machine within the decade. IBM put quantum on the cloud, builds Eagle and Osprey-class processors, and grows the software stack with Qiskit. IonQ and Quantinuum advance trapped ion qubits, high stability and fidelity that could hasten fault tolerance. Rigetti scales superconducting systems via the cloud. Microsoft pursues topological qubits for built-in robustness. China's Alibaba and Baidu, USTC, Europe, Canada, and Australia fund programs across superconductors, ions, photons, and silicon spin qubits. Multiple approaches, shared breakthroughs, and healthy competition make a vibrant, rapidly evolving field, where breakthroughs can come from anywhere at any time. In 2025, we're in the NISQ era. Small, noisy devices, powerful enough to be interesting, too error-prone for most practical tasks. We test algorithms, probe quantum mechanics, and learn to mitigate errors. Quantum simulation is promising now. Modeling molecules, hard even for supercomputers, on real quantum devices. In 5 to 10 years, targeted quantum advantage may emerge for specific, commercially relevant problems. Chemistry and materials lead, simulate interactions to design life-saving medicines and ultra-efficient catalysts. Looking ahead, logistics, finance, and energy are massive optimization problems a fault-tolerant machine could transform. Expect efficiency gains, billions saved, and reduced environmental footprint. Quantum machine learning may accelerate training and reveal hidden patterns, powering breakthroughs in diagnosis, fraud detection, and discovery. The path is hard. Decoherence threatens fragile qubits. Magnetic fields, vibration, temperature changes all inject errors. We build isolated cryogenic environments, colder than deep space, to preserve quantum states for fractions of a second. Quantum error correction encodes logical qubits across thousands or millions of physical qubits. Scaling precise control is the next decade's challenge. A mature quantum computer is not just faster, it's a new tool to unlock quantum secrets and design our world. Imagine perfectly simulating proteins, discovering room temperature superconductors, and pulling carbon from the air. We are early pioneers. The road is long, but the quantum dawn is a future worth striving for.